SwayamPrabha. Digital India. Educated India.
Good morning and welcome back. So, we discussed about the functional decomposition in the last class. We found that a functional decomposition is basically to identify the small sub functions needed in a product in order to meet the requirements of the product function as well as to meet the customer satisfaction. And we found that there are different methods to do the functional decomposition, and one of the methods we discussed was FAST, or the function analysis system technique. So, as you can see here in this screen, the first method basically try to identify all the functions within the product, assuming that there is something provided as an input to the product and something is coming out as a output. So, what is coming out as an output is considered as the top level function of the product, and what is given as input is that what you provide to the products, so that the product will be able to provide the outputs. Now, whatever is happening in between these two lines is known as the product functions or the sub functions needed in the product, and in first method we try to identify this by asking the question how or why. How something is happening in the product, by trying to answer that you will be able to get the critical path function, which we mentioned this as these are the critical path functions, and these critical path functions leads to the sub functions associated with each critical path function. So, by looking at each one of these you will be able to get all the functions needed in a product. So, this was what we discussed in the last class, and we saw that the main functions may lead to some unwanted functions in the product with something like generate noise or generate heat, and that will lead to additional functions also, which may need to compensate for the additional compensate for the unwanted functions. And then we will be having something like objective, project objective, all time functions and one time function. Like this we will be having additional functions also. By this way we will be able to get all the functions needed in a product in order to meet the main function or the top level function of the product. And once we identify these functions, we will be able to create a function tree. A function tree is one, you will be having the top level function at the top, and then we will try to identify the main functions needed in order to get the top level function, and then we go for the all sub level functions at the bottom level, and then create a tree structure with all the lower level functions coming at the lowest level of the tree. So, any functional decomposition will effectively lead to this kind of a function tree, and that function tree will be able to, we will be able to use this function tree in order to design the product at a later stage, because we will be able to identify what are the sub functions needed or what are the modules needed in a product in order to meet these requirements, and then under that what are the functions that can be identified. So, this is an example for the function tree for an electrical screwdriver, which when we do the functional decomposition we will be able to identify all these functions and then create the function tree. So, this was what we discussed in the last class. Just to give you one more example about the functional decomposition or the function tree. So, this is an iron box, electric iron box. So, we can see that in the electric iron box the top level function can be assumed as straighten out clothing. So, that can be considered as the top level function. You can have additional things also, and then smooth out wrinkles will be the way how you can straighten out the clothing. And in order to do the smooth out wrinkles, you can see that there are many things what we needed. One is that you need to maintain the base plate temperature, you need to generate the steam, and then you need to exert pressure, and you need to have a base plate which can actually provide the necessary pressure, temperature, and then remove the wrinkles. So, these are the functions that is needed, and then you can actually divide this into smaller modules or the smaller functions, and that will be getting as switch base plate temperature, hasten heating, generate heat, make base plate temperature uniform. So, unless you satisfy these functions, this function will not be able to provide the necessary outputs. So, if you have to maintain the base plate temperature, you need to have some kind to switch the temperature, you need to have the heating control or the speed at which the heating take place, and how to generate the heat, and how to make the temperature uniform at the base plate. So, if you satisfy these functions, you will be able to satisfy this, and if you satisfy this, you will be able to satisfy this. So, this is the way how you can actually identify the functions needed in a product. So, what is the importance of identifying this? Because if you are trying to design a new product, a new iron box, and you find that in the existing products there is a problem with the heating, then you know out of this which function is the one which creates the problem, and then you can take out that function and then try to identify a new method to satisfy that function, because this only function, how you actually provide that in the product depends on what concept you are using, and therefore you will be able to modify this function in order to improve the product. So, you do not need to improve all the functions in order to change the product, you can see identify which function is the one which actually creates problem, and then you will be able to modify it and then get a new product. So, this is the way how we use the functional decomposition at a later stage to improve the design of the product. Similarly, to generate steam, what are the things you need? You need to store the water, you need to generate steam, you need to facilitate addition of water. So, you have to add water, you have to store water, and you have to convert that into steam. These are the requirement of generate steam. Okay. So, this is the way how you will look at the functional decomposition and create a function tree for a product. Okay, so that is about the first method of we discussed about this fast methods, and one important question you will be having is, okay, how do we actually know that these are the where actually I need to stop? Should I actually go further and then do the decomposition? So, when will I know that I do not need to do the further decomposition of the product, for the function? And for to do that, we will actually have something called a functional common basis. So, we will try to answer this question, small easily solved sub functions, by having something called as a functional common basis. So, this is a set of well defined function verbs and flow nouns. So, we have a function verb and a flow noun, and then that can represent the products across product domains known as functional common basis. So, across the domains we will be able to use this functional common basis, and then we know at what level we will be able to stop, because if you can actually represent it as a simple verb and a noun, and that is a well understood function, then we do not really need to go further down for decomposition. So, this is the purpose of having a functional common basis, and moreover it is irrespective of the domain. So, it can be electrical product or a mechanical product or a hydraulic product. We use this common basis to represent, and therefore it does not really matter what is the domain, we can still use the same kind of a verb and a noun to represent the function. And we know that with some experience we will be able to know that, okay, oh, this is something which is commonly available and we do not need to go further decomposition. And the advantages are basically a common vocabulary. So, as I told you, independent of the domain you can have a common vocabulary of functions, and then you can have a robust vocabulary for expressiveness of a designer. So, it is very robust, so that any designer will be able to understand and represent the function using this vocabulary. And across domains you can compare the products and functions, and level of detail that when reached stops the decomposition process. So, when you can actually reach to that level, then it says that you do not need to further decompose. So, you can actually, if you can actually represent it in a common functional basis, that shows that you do not need to further decompose it, because it has already reached a stage where we have the required functions or required decomposition stage achieved. So, this is the purpose of having a functional common basis. Let us see some examples of this common basis. So, for channeling of something, whether it is channeling of a material, energy, or whatever it is, we use the terms called import, export, guide, transfer, receive, etc. So, transfer power or guide material, export material or import material, receive material. So, these are the ways in which we can represent the channeling of material, energy, or whatever it is. Similarly, to support we will say the stop, stabilize, secure, couple, mix for connection. So, connecting of two objects or two substances. You can have a couple solid or couple liquid or whatever it is. So, you can actually mix liquid, couple solid, etc. Then you can have branching of energy or materials, we can say separate or distribute. So, separate solid and liquid, or separate larger size and small size grains, etc. And then provision is store, supply, extract. Control is actuate, regulate, change, convert. Then sense, indicate, display, measure, etc. For signals we use sense signal or display signal or measure signal. These are the common terminology you will be using. So, if you use this kind of terminology, then actually it is a common basis or functional common basis. So, the basic functions are actually expressed using these functions. So, basic functions are expressed using these terminologies. Okay. So, import, these are the verbs which can be used to represent the basic function. So, once you reach the level of this detail, then you know that okay, there is no need to further decompose it. That is the purpose of using a functional common basis. So, whenever you do a functional decomposition, you need to ensure that you are using this terminology, and then you know where actually you have to stop once you reach the required level of detail. Okay, so that is about the functional common basis, and now we saw that one of the functional decomposition method is known as the FAST. And there in the first few examples we did not use the functional common basis, but hereafter in all the methods we will be using the functional common basis to identify the functions. Now, in the FAST method, the function analysis system technique, we try to find out a critical path function. So, we between these two lines we identified the outside is inside, here it is input and this is the output, and whatever is there in the critical path is known as a critical path function. So, this FAST method is useful when you have one critical path function or one critical path. So, some of the products or most of the products will be having more than one critical path. It may be doing 2 or 3 things simultaneously, and all the 3 may be critical in that particular product. So, for such products, this FAST method may not be a suitable one. So, we need to have a better method or more robust method which can actually take care of all the products or products with across the products having multiple critical path, or there are multiple critical path, and then there are multiple kinds of materials going inside, and it is not a very simple product, it is much more complex product. For such products we cannot use the FAST method, and therefore we need to go for a robust method which we call it as the function structure approach or function structure method, or sometimes it is known as a flow method also. So, the functional decomposition using flow methods. So, this is the most commonly used method whenever the product is slightly complex and there are more than one critical path, then you can always go for a flow method. And the flow method is applicable to all the domains. So, it uses independent of the domains, you will be able to use the same kind of functional common basis to represent the function. So, that is the advantage of having a flow method. So, we call this a system approach also, because in this approach we consider the product as a system. So, we consider this as a system, or we call okay, this is the product, and we assume that something is going inside to the product and something is coming out to the from the product, something is going into the product and something is coming out of the product, and this is the black box where things happens inside. And as a user we will not be knowing what is happening inside the black box. So, we are not worried about what is happening inside, right. So, when I have this product I do not really worry about what is happening inside. I know that if I give an input I will get an output. So, for me it is a black box. If I do not know the technology inside, it is a black box. So, same way we can assume that initially, oh okay, the product is a black box, you give something as an input, you get something as an output. So, for example, in the case of a washing machine, you put soap powder, water and then dirty clothes and then you switch on. So, that is all. and you do not know what is going to happen, how is it cleaning and all, and finally at the end you will get clean clothes and then dirty water and things like that. So, we can say that okay, what any product you give something as an input and then something comes as an output. Now, if we can actually find out what is happening to the input and how this input is getting converted to an output, then we will be able to tell what is the function inside or what are the functions happening inside. So, that is the approach taken in the flow method, where we assume that there are many flows taking place into the body, into the product, and there are many flows coming out of the product also. And then these flows, we assume that the one of the flows is basically energy. So, any product or most of the products will be having some kind of energy as an input, it's electrical energy or mechanical energy or human energy. Some energy will be going inside the product, and in addition to the energy there will be something called some other input will be the material. So, we say that okay, there will be some materials going inside. Depending on the product, this material may change. In the case of a washing machine, you know the materials are soap powder, water and then dirty clothes. So, these are the materials which is going inside. Or in the case of a toaster, it will be the bread as for toasting, that is going as an input to the toaster. So, same way you will be able to identify the material, what are the materials going inside. For example, you take the printer. If you take the printer as a product, what you are giving is a paper as an input, that is all what you are giving material, and then you get paper as an output also, right. So, we can get the materials, what are the materials going inside, and then we assume that there is one more input which we call it as the signal. Some signal will be going. So, this signal is more like a control signal, okay, you want to, it is a switch on or off, the toaster is on or off, printer is connected to the computer or not. So, these are the signals that will be going inside to the product in order to make the product do its function. So, without this signal the product will not be able to do its function. So, that is known as the signal. So, it is an information given to the product in order to make it do its function. So, that is the signal. So, we assume that these are the three flows going into any product. Any product you take, you can say that there can be three inputs, one is the energy, other one is the material and other one is the signal. And we assume that because nothing stays inside the product, everything comes out. So, whatever energy you give, the energy comes out, it is not staying inside. So, there will be an energy coming out, there will be material coming out and there will be signal coming out, and this will be in a different form. The same, it is not the same material which is coming out, the material may change its shape or size or its quality or whatever it is. So, some material go inside and it comes out as something else, but it is a material. So, material is going inside and material is coming out, energy is going inside, energy is coming out, and signal is going inside, signal is coming out. Now, once we assume that this is the black box and these things are the flows goes inside and the flows are coming out, the question is that what is happening to this material energy and flow is the function of functions inside the product. So, whatever happens to this material energy and flow inside, those are the functions of the product. For example, okay, so material is energy is normally represented using a single arrow, and material is represented using a double arrow in order to make it distinguished from the other one, material and energy, and signal is represented using a dotted arrow. So, this is the energy, this is the material and this is the signal. So, here you get the energy output, you get the material output and you get the signal output. Now, as a designer, what we need to look at is, okay, I am providing an electrical energy here and then this is coming out as a sound or heat, that is energy. So, I am giving energy, electrical energy as an input and it is coming as a sound energy and heat energy. So, what is happening to this, or what are things happening to this energy and how is it coming out as a sound or heat. So, all those things what happens to this electrical energy inside this are the sub functions of the product, or we can decompose those functions which actually convert the electrical energy to sound or heat using this. Similarly, what is happening to the mechanical energy, sorry, the material. So, I am giving water and clothes, and then how is it coming as dirty water? I am giving good water and soap powder, how is it coming as a dirty soap water? So, what is happening inside in order to convert this water into a dirty water? Similarly, clothes, I am giving dirty clothes, I am getting a clean clothes. So, what is happening to the clothes inside in order to make it clean? All those things what are happening inside this box are the functions of the product. So, this is the way how we decompose the product functions using the flow method or the function structure methods. Similarly, the signal also, we will be giving an on off signal, and then finally you will be getting a signal saying that okay, cloth is complete and the washing is complete. So, that is a signal coming out. When you are giving a on signal, you are getting output as either it is an off or it is some noise or whatever it is, you are getting as a signal saying that it is complete. So, you will be getting an input, you will be giving an input and you will be getting an output, and this the relation between this input and the output, and what is happening to this input as it passes through the product are the functions in the product, and this is basically known as the black box approach for functional decomposition or the flow method of functional decomposition. We will take a few examples to make it more clear to you. So, as I mentioned, we consider the product as a black box and then consider the input as a flow. There is a flow going into the input and going to the product, and there is a flow coming out of the product, and these flows we assume that these are the energy, material and information or the signal. Okay, and then the energy, material and information. So, information and signal, I mentioned the signal, it is information. So, that information in the form of a signal, you will be getting the energy, material and information going, and then energy, material and information coming out. And what is happening to this energy? So, as the energy is going, and then in this box it actually passes through many functions, okay, transmit energy, convert energy, and then generate heat. So, many things will be happening there, and finally coming out as generate noise or heat or whatever it is, this will be coming. So, what are these functions we need to identify? Similarly, the material will be coming inside. So, we see okay, material is accepted, then transmitted or coupled or mixed, and then doing something and coming out. So, there may be interaction, this may be coming here and this may be going here. So, we need to look at all these and then see what are these functions and how the material is coming out in a different form. So, this is what is the flow method of functional decomposition. Oops. Okay, now what are these material, energy, and I already explained it. So, information gives the internal decision making capability. So, the information or the signal gives the internal decision making capability, and the term signal is often used to express the physical form in which the information is conveyed. So, signal is the common form in which the information will be normally conveyed, and signals are prepared, received, compared, combined, separated and transmitted, displayed or recorded inside the product. So, the signal can actually be transmitted or recorded or displayed, it can actually happen many things inside. So, we need to find out what is happening. And the materials are the gas, liquid, solid, dust, raw materials, workpieces, components. So, anything can be a raw material going into the product. And then we have the energy. The energy is the ability to make something happen. So, electrical, kinetic, magnetic, heat, etc., etc. So, this is the way in which we try to identify the flows into the product and then find out what is the flow coming out of the product. So, let us take a simple example of an electrical screwdriver and see how can we actually identify the functions inside the product using the flow methods. So, we will take this as the product, electrical screwdriver. So, the purpose of an electrical screwdriver is basically to loosen or tighten the screw. So, we will write the main function loosen or that is what we know. the fix screw or remove a screw. That is basically the purpose of an electric screwdriver. An electric screwdriver is normally used by a human. So, it is actually a hand operated electric screwdriver. Okay. So, that is the screwdriver we are talking about. So, loosen or tighten screws is the function. Now, we need to see what are the flows going into the product. Okay. So, what are the flows that we can think of? So, it is an electrical screwdriver. So, the energy, first we look at the energy. So, of course, electrical energy is the one going inside, electrical energy is there, and then as I mentioned, it is a human operated one. So, human energy is also used in the process. So, it is not only electrical energy, we have the human energy also, we call it as the human energy, what actually we apply as a user, what we apply it is the human energy. So, we can say that these are the energy going inside. Now, what are the materials going inside? So, we can actually see what kind of materials are normally gone inside in this. So, one may be a tool bit. So, we may have to have a tool bit in order to screw the bit. So, a tool bit will be used, and then maybe screws, we will be using screws to fix something. So, the tool bit and screws may be the materials going inside. And then what is the signal or the information? So, one information is that you want to tighten or release the screw, okay, you want to loosen or tighten the screw. So, that is the information. So, maybe the status of the screw, whether you want to tighten or loosen, and then whether it is on or off, whether the screwdriver is on or off, power supply is there or not. So, these are the information that will be going inside. And then what are the things coming out? Okay, when we use this screwdriver, you will see that some energy will be coming out. So, what are this energy coming out? So, one may be when you use this screwdriver, lot of noise will be produced. So, sound energy is something which you can expect. There will be a sound energy, and there will be vibration, so vibrational energy or mechanical energy, and then there may be heat produced. So, these are the energy that you can see. So, the electrical energy is converted to sound energy, vibration energy, heat energy. So, that are the energy that you can think of. And then here, what is the material? So, the tool bit may come out after you use, you can actually take out the tool bit from the screwdriver. Similarly, if it is unscrewing, then you will be getting the screw also as an output. So, these are the material that you can get as output from the product. And then the signal, again that is on or off you can get, and whether the status also, whether the screw is tight or loose, that information also can be obtained. So, you can see that in order to loosen or tighten the screws, so we will be giving this as the inputs, and then we will be getting this as the outputs. Now, as a designer, we need to know how this electrical energy is and human energy is used to loosen or tighten the screws, and then finally the bit and the screw comes out, and this converted to sound and vibration, and then we get the signal also here. So, what is happening inside as the flows goes to the product and it comes out? What is happening in between or what is inside it happening, we need to find out, and that can be done by following the flows. So, we will take electrical energy and then see what is happening to the electrical energy inside, and at what stage it is actually getting converted to heat, noise or vibration. Similarly, at what stage the tool bit is going inside and what is happening, and how the tool bit is helping to fix a screw and then come out as a tool bit itself. So, these are the things what we need to look inside the product in order to identify the functions. So, let us look at that and then see how we can represent it. Okay. So, we will get this as the loosen or tighten screws. So, electricity and human force as the input, and then screw tool bit and hand, okay, hand also as a material will be going inside, and then loose or tight or on or off will be the information, and we will be getting the tool bit, screw and hand, heat, noise, vibration, and loose or tight or on or off as the material. Now, we need to see what is happening inside. So, what we will do, we will try to explore this box and then see each input. Now, we will see okay, this is the electrical energy. So, I will start with electrical energy and try to find out what is happening to the electrical energy and the forces, human force, electricity, screw bit, tool, etc. So, what I will do, I will try to see what is happening to the electrical energy. So, now I can identify, okay, I take the electrical energy. So, and if there is a storage power, I mean if I assume that it has got a stored battery storage, then I will say that okay, I need to store electrical energy. So, first I will store in the battery, and then I will supply electricity to the so, I am using the functional common basis, store electrical energy, supply electrical energy, and then I will say that I need to actuate it, I need to on or off, I need to switch on or off in order to make the product work. So, that is basically I am actuating the electricity. So, what I will say, I will actuate electrical energy, actuate electrical energy, and then I will say that okay, I switch on or off, but then I need to control the energy or control the motion of the tool bit, because I need to, if I have to go to forward direction or reverse direction, I want to change the speed, increase the speed or decrease the speed, I need to have some kind of a control over the power. So, what I will do, I will have a regulate electricity, I can regulate electricity. Okay, so, I will be regulating it, and then what I will do, I will be after regulate, I can actually convert this electrical energy to mechanical energy. So, I will convert the electrical energy to mechanical energy, and then I will transmit the mechanical energy. Okay. So, the electrical energy is coming, and then it is going through all these functions and getting converted to mechanical energy and transmitted as mechanical energy. So, that is what actually happened to the electrical energy, and when it is converting to mechanical energy, then there will be something called generate heat or generate noise. So, these are the unwanted functions, and then the noise goes as an output, heat goes as an output. So, you have the noise as an output and heat as an output. If you have a cooling mechanism, then there will be transmit heat also, because you are transmitting the heat to outside the product. So, there will be transmit heat. Normally in the screwdrivers you do not have any special mechanism for heat transmission. So, we will say that just heat is just coming out. So, you know that now the electrical energy is converted to noise and heat because of these functions. That is what actually happens here. Similarly, okay, now this has to happen. Now, we have to see the, okay, the next one is basically the material. So, we consider the material going inside. Assume that the tool bit is considered here. So, we assume that there is a tool bit going inside. So, we need to do this tool bit. So, the tool bit is taken, and then we will be using our hand also. So, hand also is a material, it is going inside. So, the hand will be coming. So, you will say using the hand. So, you will be using the hand for many things. One is basically to actuate electricity and regulate electricity. We will be using this because we need to have the human hand to do this. So, we will actually say that there is a connection here. Similarly, we use the tool bit. So, we need to couple the tool bit. So, we will say that we couple the bit. So, couple basically you connect the tool bit to the screwdriver. So, that is the couple the tool bit, or we call it couple solid, because it is these are two solids. So, we will say that couple solid to use the functional common basis. So, couple solids, and then when you couple that, you are actually connecting them, but it is not only sufficient, you need to secure it also, you need to lock it, otherwise it will come out. So, you need to secure solids, and these are done using the human hand as a input. So, without human hand you will not be able to do this. So, these are materials. So, secure solids, and then we will have separate solid. So, you need to separate it later. So, after the function is over, you need to separate it. So, you need to separate. Separate solid, and then the solid will actually go out. So, you are getting the tool bit coming out, because it is already separated from the solid, separated from the machine, and then it got, and again you need human hand to do this. So, this is the way how the bit comes out. So, your tool bit is coming out after separating from the machine, and this way you can actually look at each one of the inputs and then see what happening to this input. So, you can actually look at now the screw also, you have the screw, and then we need to okay, we will be identifying all those functions connected this, and then how the screw is coming out, that also can be identified, something similar to this. And in between we have to see, oh, what actually happened to this transmit torque. So, we already transmitted the torque, now what actually we did with this. So, we need to have a rotate solid, because the solid needs to be rotated. So, there will be a parallel function coming from here, rotate solid, and this rotate solid will be connected to the transmit. So, the transmit power will come, and then this solid will be rotated, and that will actually move the screw in or out. So, we will be able to identify the functions by going through each flow and then identifying what is happening to this flow as it passes through the product and coming out. So, this way we will be able to identify all the sub functions needed within the product in order to convert the input flow to the output flow. And if you are not able to see the output flow this side, that means you have missed some function and you need to go through it and then try to identify the function inside. So, this is the way how we get the or do the functional decomposition in the flow methods. I hope you understood this, and I will take this as a more detailed one. I like show you the detailed explanation. So, this is the input, as I showed you the input going and then output. So, as I told you, the tool bit is coming, and then couple solid, secure solid, and separate solids. Okay. And we will be using the hand, using hand and human force to do this. So, we need to have the hand and human force to do the solid, couple solid, secure solid, and separate solid. That is where the human energy is coming as an input. So, human hand and energy coming together to help this couple solid, secure solid, and separate solids. And again we will be using the human force for regulating the orientation of the tool. So, we need to because we are holding the drilling this screwdriver. So, we need to orient it as per the requirement of the operation, because we cannot simply always having a same orientation. We use our hand and the hand force to orient it, that is basically regulate orientation, and then regulate translation, because we need to move in and out in order to tighten or loosen the screw. So, that is basically regulate translation. Okay. And then the human torque will be used for source rotation and convert the force, because we need to rotate it, and then that is the source rotation, convert the force. Then you change torque, that is for the clockwise or anti-clockwise direction, then transmit torque and rotate solid. So, the rotate solid is basically you have a screw, and that screw will be attached to the body and body of the surface where you want to screw it, and then you rotate the solid, then the turning screw will happen. And this electricity store, supply, actuate, regulate, convert to rotation, and this torque will be coming, and this change torque, and then you will be getting the transmit torque and then rotate solids. and you will see that this bit is already attached to the machine, and then when you rotate that you will be getting the required torque to move the screw in or out, and you will be getting the screw either it going into the system or coming out of the system. So, this is the way you will be able to see all the functions within this box seeing. So, these are the inputs and these are the outputs that you can see, and you will see that heat and other things are coming out as a output from here. So, this shows the functions can be identified by following the flow. Each flow can be followed and then try to identify what happens to that flow, and from the starting to the end until it comes out. If you are able to follow it and then identify all the functions needed to convert that into the output, then you get all the functions needed in the product. So, that is the basic principle of functional decomposition using flow methods. I hope you understood this, and using this you will be able to decompose any complex product, because we are not worried about what the product is, we are worried about what is going in and what is coming out. If we know these two, then we will be able to identify what happens inside, and that actually tells you how to get the sub functions within a product. And once you have this, you can actually create the function tree and then see how the functions are arranged as in a proper way, so that we will get the top level function, then the sub functions, and the sub functions can be easily identified, and that helps you to design the product also. Okay. Yeah, so this is the function tree, which actually from the previous functional decomposition you will be able to identify all those functions. Now, you can see all those at the bottom level, you can see couple, separate, solid, import, hand, import, human force, torque, rotate, transmit, etc. All these can be identified using this methods. Okay. So, this is another example for the inkjet printer. So, we are talking about the printer, and in the printer we will see that the main function is make the hard copies or soft copies of the product document, and the inputs are the electricity, human energy, ink and paper, and here you have this heat, noise, kinetic energy, printout, printer status and ink level. So, these are the inputs flows and these are the outputs. So, you can see the energy is expressed using a single arrow, and this has a thick arrow and a dotted arrow. Now, if I go through this decomposition, I can actually make the product. So, within this box all the functions can be represented within this box, and we will follow each one each input one by one. So, look at the paper. So, you take paper, so import paper and store paper. Okay. If there is a storing facility, you can store it into paper in the printer. If not, there will not be, the store paper will not be there. And then choose paper. So, depending on the paper and the number of copies, the paper is to be chosen, and then feed or increment the paper and deliver the paper or store the printout. So, that are the, these are the functions that can, these are things what happens to the paper when you put it inside, when you give it as an input to the printer. Now, there is a feed and increment the paper. So, we need to have some input to do that. Okay. So, we will see what is there. So, when you are storing paper, then there should be something to handle the load also. Okay. Then we will see the ink. So, import ink and store ink. If it is an inkjet printer, you need to have some ink stored. So, that is import. Import is bring in the ink and then store it. Then jet ink, that means you have to convert that into a jet, and then you have to display the ink level also. So, that is an information that you need to see based on the store ink, you will display the ink level, and that will be going as an output signal or the information. And if there is storage, then you need to have a handling load also, support handling loads, and the reaction force will coming as an output here and here. Then electricity, connect electricity, actuate electricity, supply power, convert electricity to mechanical energy. Okay. And that mechanical energy is used for here for incrementing the paper. So, now we know what is happening to the paper and what is happening to the electricity. When you convert the electrical energy, there will be noise generated and there will be heat generated also. So, heat, noise and vibration may happen depending on the type of conversion, and then you have the process data, that is the data that is coming as an information. So, you have the input data coming as an information or a signal. So, you have to process this information and that will be given to different functions in order to make it possible that function to happen. For example, to choose paper or the feed the paper, you need the information from the controller. So, that is the process data will generate the signal, necessary signals for the ink generation, ink jetting, paper choosing and feeding the paper as well as delivering of paper. So, this is the information flow taking place in the product. And you will be able to see the capture vapor. Suppose you want to have a system where the jetting produces some kind of vapor. So, you need to have a capture vapor as a additional function. Okay. So, air will be used as an input. In that case it will capture vapor and then it will filter the flow and then hot air and vapor will be coming out. So, that is why you are getting hot air, because you are taking air inside and then use it for some purpose inside and then the hot air is coming out. Okay. So, this shows the detailed diagram of the same inkjet printer, and you can see that the inkjet printer has got many functions inside, as you can see here, and all these functions can be easily identified by looking at the inputs that is going into the product and the output coming out of the product. And this method of looking at the flow and then trying to understand the functions inside the product is the function structure method of flow function decomposition, or sometimes known as flow method of functional decomposition. Okay. So, the last example for today is the electric pencil sharpener. As you can see here, electricity is going inside, hand is there and pencil is there, and you get the vibration as an output, noise as an output, and then the sharp pencil as an output, and some gravity forces will be there, and the shavings of the pencil will be coming as an output. Now, what is happening to the electricity? Import electricity, actuate electricity, convert to rotation and change rotation energy, because you can change the direction of rotation if needed, and then if the, since it is vibration generated, you have dissipate vibration also. And pencil, import solid, send solid, guide solid, transmit the rotational energy, because you are generating rotational energy, you transmit the rotational energy here and then separate solids. So, you are saying that you have to separate solid from another solid. So, pencil is taken and pencil is sharpened by removing the material from the pencil, that is the separate solid, and then export solid. Thus, shaving the pencil is exported, the pencil after the sharpening it is removed, and this shavings or the dust coming out of the sharpener will be guided to store somewhere, and later on it will be exported or sent out, that is the coming out as the shavings. So, this way by the last one is the hand, how the human hand is used. So, human hand is used for holding the pencil, importing the pencil and then guiding the pencil, and similarly for exporting the solids we use exporting the pencil and exporting the solid, we use the human hand. So, you use the human hand and hand energy and use that one to hold the pencil, remove the pencil as well as remove the shavings also. Okay, so, that actually explains the way in which how we can use the flow method of functional decomposition to identify all the functions within the product. Okay, so, I will stop here. We will take a few more examples in the next class and then see how we can use the functional common basis and the flow method to identify all the sub functions in the product. Okay, yeah, thank you.